All right, in this video we're just going to go over this page in our workbook, page 208. It's called Sandcastles. Let's read it. Oceana loves to build elaborate sandcastles. Her problem is that her castles take a long time to build and often get swept away by the incoming tide. Oceana is planning a trip to the beach next week. She decides to pay attention to the tide so she can plan her castle building and have as much time as possible. The beach slopes up gradually from the ocean toward the parking lot. Oceana considers the water line to be high. If the water comes farther up the beach, leaving less sandy area visible, she considers the water line to be low if there's more sandy area visible. So high means water, low means sand. Oceana likes to position herself as close to the water as possible because damp sand is better for building. According to Oceana's analysis, the water level on the beach for the day of her trip will fit this equation. This is a very important equation. In this equation, W of t represents how far the water line is above or below its average position. It's all relative to the average position. The distance is measured in feet, and t represents the number of hours elapsed since midnight. So t is hours since midnight. Great. Okay, so let's just, before we go to the next page, because our questions are actually asked on the next page, let's just take a minute to understand what's going on. So there's a parking lot somewhere. Let's see, maybe I can draw a nice little, here's your parking lot where all of your cars like to park on, right? There you go. A couple cars in the parking lot. And then you can walk down into the sandy beach. That's sand, by the way. And then water comes up. Oh, I'm drawing the waves leaving the beach, but whatever. There's your water level. So on average, let's say that this right here is where our average tide line is. And then if it's high tide, that means the water level is high. So we might say this is high tide. And then we might say way down here, if the water level is really far out, this is called low tide. Oceana likes to build her sandcastles close to the edge of the water because that's where the sand is wet, and wet sand makes good sandcastles. And we're given this equation here, 20 times the sine of 29t, that represents it, right? Because really what happens, it's cyclical, where like the water level will come in and then go out and then go up and then go down and go up and go down. And even though this isn't a Ferris wheel like we may have studied in our class before, it's still cyclical in a sense. And we'll see that on this next page as we start to play with some of the graphs. Okay. In the case shown in the diagram, the water line is above its average position, and the water level is positive. Okay, meaning, actually just don't like the picture the book gives us. So that means that a high tide is going to have positive values, and a low tide is going to have negative values, because it's all relative to this average line, meaning the high tide is going to be some positive amount of feet above the line, and the low tide is going to be some negative amount of feet below the average tide line. Okay, great. First things first, we're going to graph the water line function for a 24-hour period. Okay, let's see, can I scooch this over? Scooch, scooch, scooch. So let's do it. We know that our water line as a function of time is modeled by the function, did I give it to us on the other page? 20 times the sine of 29t. Okay, if we compare this just to something we've been familiar with, like our Ferris wheel thing, we know that our Ferris wheel has a general equation of height as a function of time is equal to our center height plus the radius times the sine of, and we've made it more complicated in here, but we're taking the sine of an angle, right? We're measuring some angle. So let's think about it, this Ferris wheel one, in terms of this new ocean one that we've been given. Well, our Ferris wheel has a starting center height, right? Because our Ferris wheel is lifted off the ground. This one's starting height is the average tide line. And what we just talked about is that the average tide line is 0, meaning we're not saying there's no center height to be raised off the ground. It's only the average tide line, which means we've got no C plus. It's just, that's it. So our C in this case up here would be 0. Our radius for our Ferris wheel, it goes right here and multiplies the sine of whatever angle we've got. So we also know that the highest the Ferris wheel can go above the center height is the radius, which means that we can actually transfer that over here. The highest the ocean, the tide line, the water line can go above its average height is this number right there. So we already know just from looking at this that the high tide is going to be 20 feet above the average water line. So let's write that down. High tide is going to be 20 feet. Low tide, very similar, is going to be negative 20 feet, right? Because it's the negative values are below average and then the positive values are above average. Okay, so we're already starting to get a little bit of information. And then I guess we could write this out here, but the average tide is going to be 0 feet, right? Because everything is based off of this average tide. Okay, with this information, that's actually enough to get us started to graph this. It said to graph the waterline function for a 24-hour period. So let's go from, we'll just draw a big old long line. We know that, let's see, this is going to be our graph. But let's do a couple let's calculate a couple values to kind of figure out where our tide starts and which way it's going, whether it starts going down, starts going up, if it starts up high, starts down low. Let's figure out what time it is right at 0 hours before midnight. And I guess we can maybe label this, yeah, because we're doing a 24-hour period. So then halfway there is going to be 12 hours. And then cut that in half again, that's going to be 6 hours. And then if we cut that in half again, that'll be 3 hours, 9 hours. Let's see, do that one, that'll be 18, 15, 21. And let's just pause. We don't want to make it too busy. The other things we know is that our max tide is going to be 20 feet, and our minimum tide is going to be negative 20 feet. Okay, so let's do a little in-out table where t is the number of hours, and so let's do 0, 1, 2, 3, 4, 5, and let's just try up to 6 hours, let's say. And let's get a tide line for all of those 6 hours. So this is starting at midnight and then going to 6 a.m. Okay, so I got my calculator out here. So you can see it. And what we're going to do is we're just going to use our function right here, our 20 sine of 29t. So 20 times the sine of 29 times t. So t is 0 to start off with. And our answer is it equals 0. So let's write that in. 0. Okay. Oh, look at that glare. Let's get that out of there. Okay, now let's try for 1 hour. At 1 hour, it's going to be 9 point, and I'm just going to round it to the tenth, to a tenth of a foot. So 9.7 feet. At 2 hours, it's at 16.96, so 17.0 after we round. Then at 3 hours, it's going to be at 20.0. Hey, that rounds up to our max. At 4 hours, it's going to be at 17.97, so then 18.0. And then at 5 hours, it'll be 11.5, and then 6 hours. Oops. Look, we're getting down. 2.1. Oh, let's go. You know what we're going to do? We're going to just do a lot more. Time, water line, 7 hours, 8 hours, 9 hours, 10 hours, 11 hours, 12 hours. Because this is really easy calculating. Excuse me. 7 hours, we're going to have, ooh, look, now we're below average tide. So negative 7.8. For 8 hours, it's going to be negative 15.8. For 9 hours, it's going to be negative 19.8. Look, and this is pretty close to our low tide, right? Because our low tide is negative 20, or right there, negative 20. Okay, let's try 10. That's negative 18.8. Then negative 11 is going to be negative 13.1. Negative 12 will be negative 4.2. Okay, let's pause with calculating and let's just plot some of these points. Okay, I'm going to add, I guess I'll add a couple of tick marks here. Boop, boop. Cutting our spaces into thirds so that we can see our hours when we plot them. Another thing I like doing is I like to just kind of draw a dotted line that represents our max tide and our minimum tide. And that kind of helps me graph a little bit better because we know it's if this is going to be a sine function, we know it's going to go up and down, up and down, up and down. So at 0 hours, our average tide, it is our average tide. So we're going to put a dot right there. At 1 hour, we're at about, let's see, I'm going to make a couple other reference points. That's 10 feet. Here's negative 10 feet. At 1 hour, we're going to be just under 10 feet. At 2 hours, we're going to be at 17 feet. So what is that, like close to there-ish? At 3 hours, we're going to be at 20. At 4 hours, we're going to be down to 18, which is a little bit higher than this one. At 5 hours, 3, 4, 5, we're going to be at 11.5, so just above 10 feet. At 6 hours, we're going to be just above 6 feet, or just above average tide. At 7 hours, we're now at negative 7.8, so I don't know, maybe down something like that. At 8 hours, we're at negative 15, so right in between those two. At 9 hours, we're at negative 19.8, so almost all the way down. And then at negative 10 hours, we're at 18.8. Negative at 11 hours, we're at negative 13, so something like there. And then at 12 hours, we're at negative 4, so almost back to the start. Okay. And as you can see, look at that. We've got a great sine wave that we are making. And you can recognize that it's a sine wave because of its periodic function. And we could continue it and just kind of like say what it does. But we almost graphed the first period. And what I want to do is actually, instead of just picking on the hour graphs, I actually want to pick other times to graph this thing so that now instead of graphing just every hour, we're gonna graph the next time it's the average tide, we're gonna graph the next time it's the peak, the next time it's the average tide, then the minimum, then the average. So that's what we're gonna look for. We're gonna look for the times that would equal this. So if we look at our function, we see that here we've almost done a full period. Well, an exact full period is going to be 360 degrees. because that's the amount of degrees in a circle or an amount of degrees in a period, right? It's the amount of degrees it takes to make a complete cycle. So here we're going to think about this function, and we're going to say that we know that the water line is going to be, let me write out the function that we're going to use right here so I can line everything up. 20 times the sine of 29t. And so we want to find out, when is the water line going to be 0 again? Well, actually, we know it'll be 0. And the way we're going to solve for that is we're going to say, well, we know it'll be 0. Oh, wait, I'm actually doing, what am I doing? Okay. I'm actually skipping ahead a little bit. We know it'll be 0 when the angle that we have is equal to 360 degrees, right? Because that means we completed the full cycle where it'll be back to 0. So what we're going to say is, well, what do we multiply 29 by? What time do we multiply 29 by to get 360 degrees? So our goal is to get 360 degrees, and that's got to equal 29 times however many hours after midnight. Well, then we can just solve for t. So we're going to divide both sides by 29, get out our calculator again, and we'll say, what is, clear all, what is 360 divided by 29? And, right, that's our answer. So 12, which is equal to, I should write this, t is equal to 12.41. Or like 12.4, right? So we're really close. So then right here at 12.4 hours, and actually why don't we carry on this work here? At 12.4 hours, this is going to be back to 0 degrees. So let's write that. Here's 12, that's 13, so 0.4 is a little less than halfway. So now we're back to the middle. Okay, we're going to do peak, center, down, center. So 4 more. The next one, we're going to make it up to the top again, 90 degrees after, right? Because thinking about our Ferris wheel, if you're at the center line, 90 degrees higher is right there, and then another 90 degrees is right here, and then another 90 degrees is right there, and then another 90 degrees, right? And so these are the 4 points that we're going to try to plot. We could do it this way every time, just like we did, saying, well, at 360 degrees it'll be there, so then the next one will be 360 plus 90 degrees, divide that by 29, it's all good. But what I actually want to point out is, well, if we know that this is 360 as a 360 degree is the time of the cycle, the time of the period, then 1/4 of that will be our 90 degree turn. So then we just need to do 12.41 divided by 4, and that's going to get us our 90 degree period, or the portion of the period that is 90 degrees. So let's take this same number we have, and we'll just divide it by 4. And that's 3.103448827, blah, blah, blah. So I'm going to write that up a few decimals. 3.1034. Okay. So now we just need to add 3.10344 to this number. Let's do that. So let me clear some stuff. We'd say 12.4 plus 3.1034. So 15.5 is what we'll call it. 15.5. And then we're going to do that again. So I'm going to just say times 2. Then 18.6. And then we're going to do times 3. And that's 21.7. Oh, I'm running out of room. 21.7. And then times 4 gets us to 24.8. But that's beyond our time. Well, I'm going to write it anyways. 24.8, because they only asked us to graph a 24-hour period. So then, if that's the case, and we're going to prove it twice, and then we're just going to follow the pattern. If that's the case, then this should be, if we do the 20 times the sine of this, our answer should be 20 feet. So let's see if that's it. Clear all. 20 times the sine of 15.5. Oh, of 29 times 15.5. There we go, 19.999, which rounds up to 20. Then if we do 18.6. Now we're almost to 0. That actually is a little off. What if we do like 6.5? Oh no, that's too big. 18.58, 0.57, 0.55, 0.8. Oh no, that says 18.6. Did I do 18.8 earlier? Yeah, that's fine. 18.6. We're gonna chalk that one up to rounding. Oh no, we'll keep it 0.2 feet. Then 21.7 is negative 20, and then 24.8. We're back to 0, negative 0.3. Okay, so now we can graph these. So at 12.4, we got that. Then at 15.5, we're all the way back at the top. So 15.5, we're up there. Then at 18.6, oh, I have to draw my other. There's 18, there's 19, 18.6 is going to be something like right there. Then at 21.7, maybe something like right there. We're down at the bottom. And then 24.8 might end up being something like that. Oh, can you all see that? Yeah. And there we go. We've done it. We're geniuses. That's our graph of 2 periods of this work. And that's number 1. All right, let's take a look at the next ones. What is the highest point up the beach compared to its average position that the water line will be during the day? Well, we answered that one already, right? That's high tide, 20 feet. What's the lowest position that the water line will be during the day? The lowest position, that's low tide, which is negative 20 feet. Suppose Oceana plans to build her castle right on the average water line, just as the water has moved below that line. How much time will she have to build before the water returns and destroys her work? Oh, wait. Okay, so then the question is, how long will she have to build if it's if she starts building as the tide's going down there, and then it goes down and comes back up right here? Well, isn't that that's 180 degrees, right? That's half of a cycle, or 2 90-degree periods. If this is the length of our 90-degree period, then that's going to be 3.10344 times 2. So that'll be 6.20688 hours. So she started building, yeah, right? We already did that math. If you don't know how to do this, rewind. Suppose Oceana wants to build 10 feet below the average water line. What is the maximum amount of time she can have for making her castle? Okay, well, let's look at that. So 10 feet below the water line would be something like here, right? You all see that? So the question is what's the length of time from there to there? And we're gonna need a little more room. So let's get a little more room. Let's see, this is number 4. We're gonna do number 4 right here. And what we have is we see that this is our line, or our average tide line, and then let's say this right here is negative 10. That's negative 10 feet. And our question is what is the distance from there to there? Okay, there's a couple ways to do this. The first way is we want to look at this and say, okay, right here, that's low tide. do we know the time of the lowest tide? Yes, we do, right? The lowest tide, that's going to be one 90-degree period, two 90-degree periods, three 90-degree periods. So whatever the time, the number of hours is going to be 3 times our 90-degree period. So let's do that. So the low tide time is going to be 3 times 3.10, oops, that didn't draw 10344, which ends up being 9.30. Oh, I'm going to mess up a couple decimals. Let's do the calculator here. Clear all. 3 times 3.10344. 3.10, oh, you can't see that. 3.1032. 9.3132 hours. Okay. So that is the time that we've got our lowest tide. So this is 9.31032 hours. Okay. Then what we want to do is figure out, well, since this is symmetric, that means that the distance from here to here is maybe some distance x, and it's going to be the exact same as the distance from here to there, so another x. So our answer for this one is just going to be 2 times that distance. Okay, well then our last question is, what is the water, what time will the water be -10 feet? And there's a couple ways to do that. In this one, I'm just going to show you how to guess and check. In the next video, you're going to learn how to solve for the exact answer, so you don't have to guess and check. But so we can actually just kind of estimate where it is. And so we can actually use our table to find the number closest to -10. So right there, I'd say is pretty close to -10. So something like 7.5. So let's get our calculator out and then rewrite our function. 20 times the sine of 29 times 7.5. Okay, so that's a little too low, which means we've gone too far ahead in time. We need to go back a little bit. So let's try 7.4. Still a little bit too low. 7.2? Now we're getting closer. What does 7.3 look like? Okay, so 7.2, and now we want to get this number as close to -10 as we can. Let's try 7.27. Oh, too big. 7.26, 2.5. Oh, look at that. That's pretty close. 2.4. Okay, so now we're at 2.48. 2.47. I think I'm looking for 2 zeros. 2.45. 2.44. Oh, we're getting really close. 2.43. This is going to be it. There it is. That's enough for me. 7.242 hours gets us -10. So right there is 7.242 hours. Okay, so then what we need to do is just find the distance between those two, which is the difference of time. Actually, this number is supposed to be on this side. That's right here, 7.424. Okay, so what is that distance? And we can really do is just take this time and subtract that time. So the distance is going to be 9.31032 minus 7.424. And let's see what that is. Clear all. 9.3102, oops, 032. 9.31032 minus 7.424. And that is equal to 1.88. 632. Okay, but that's only this distance right there. That's 1x. We need 2x's to get the total amount of time. So then 1.88632 times 2. Let's do equals, and then times 2. Oh. 1.88632. Okay? And there's our answer. 3.77 hours. And I rounded because that's probably enough specificity. Okay, now our last problem is number 5 here. Suppose Oceana decides she needs only 2 hours to build and admire her castle. What's the lowest position on the beach where she can build? Well, we're going to use this picture here to kind of tell us that. Because this distance right here ended up being 1.8 hours. But if our x was 1 hour, then 2x's would be 2 hours, and that's exactly what we're looking for. So, let's see. I think we can maybe squeeze in number 5 right there. So then what we need is we need to know if this point right here, right, that's this low part, is 9.31 hours, then an hour this way is going to be 10.31 hours. And an hour before it is going to be 8.31 hours. So the time that we need to go from is 8.31 hours to 10.31 hours. Which means we actually know the time, which means then we can just plug everything into our function up here, just like we did on our in and out table, to solve for our answer, right? Because that we just showed that this was 1 hour, and there's another hour, and she builds it, admires it, and she's done. It washes away. So we're gonna plug in and find the water line at, say, 8.31 hours, which is going to be 20 times the sine of 29 times 8.31. And that's equal to, clear it all, 20 times the sine of 29 times 8.31. So she needs to go to negative 17.5 feet below average tide line. And that's it. This is a long video, but hopefully that helped. I guess here's the whole screenshot if you need the whole deal. Ta-da.